Gnanam Paramam Dheyam. Knowledge is supreme.
So in today's lecture, we will prove a very important theorem, so-called Kroneker's theorem, which says that given a polynomial over arbitrary field, I can enlarge this field to a finite field extension so that the given polynomial has all its roots in a bigger field. Let us recall first what we have been doing. So, K is our base field and A is a K algebra. And we have defined elements x in K, which is algebraic over K. This means the evaluation map from the polynomial ring to A, this is the evaluation map by x. That means x is mapped to the variable x is mapped to the element x, small x in A, and therefore a polynomial f will be mapped into f evaluated at x. So this is called the evaluation map. At x, and x is called algebraic if the kernel of this evaluation map is non-zero. That is, if and only if x is algebraic over K. But this means, note that this kernel is an ideal in the polynomial ring over a field K, and therefore we know that all ideals in this ring are principal. Therefore, this ideal kernel of epsilon x is generated by a polynomial mu x. This mu x I can choose monic polynomial in Kx such that this mu belongs to the kernel means mu x evaluated at x is 0. That means x is a 0 of mu x. This unique, it's unique because we have chosen it to be monic polynomial. This polynomial is called minimal monic or minimal polynomial of x over K. So if we have a field extension, if L over K is a field extension, and suppose L over K is finite, that means dimension of L as a vector space over K is finite, then we know every element of L over K is algebraic. That means the field extension L over K is algebraic field extension. So we have Kx, and suppose I have a non-zero polynomial mu in Kx. Mu is non-zero. Assume it is monic. Then we look at the residue class algebra Kx mod mu. ideal generated by mu. This is a residue class algebra over A, and let us denote X to be the image of capital X in this residue class algebra. So that means this residue class algebra is generated as a algebra over K by the small x. And when is it a field? So Kx is a field if and only if X is algebraic over K, which is equivalent to saying mu is a prime polynomial in Kx, but that is equivalent to saying mu, this ideal generated by mu is a non-zero prime ideal in Kx, but we know non-zero prime ideals in a PID are principal, so this is equivalent to saying mu is a maximal ideal in Kx. So this means, in other words, this means Kx is a field. Kx, which is the residue class algebra, Kx mod ideal generated by the maximal ideal generated by mu, this is a field. So we have a map, K is here, K is naturally contained in the polynomial ring Kx, and from Kx we have Kx modulo mu ideal generated by mu, and this inclusion, this is a natural inclusion because this K is a field and all these both these are ring homomorphism, therefore because there are no ideals other than 0 and the whole K, and the kernel cannot be the whole K because 1 goes to 1 under our ring homomorphisms. So therefore this becomes a field extension. This is, so therefore Kx over K is a field extension, and in fact the degree of this field extension, that is dimension of K over Kx, this dimension is nothing but the degree of mu, and also we know this x is a 0 of mu, that is mu x is 0. This mu x is precisely the residue class of mu, but because it belongs to the ideal generated by mu, this is 0, so x is a 0 of mu. All right. So now we come to the theorem of Kronecker, which is used very often in this course. So this is the theorem. This is theorem of Kronecker. All right. So this was proved by Kronecker around 1887. All right. So let K be a field. And capital F be a polynomial with coefficients in K. f is in Kx and f is non-zero polynomial, then there exists a finite field extension L over K such that f, which is a polynomial in Kx, also you can think of it's a polynomial in Lx, splits into linear factors, not in Kx but in Lx. That means f is of the form a x minus x1 power nu 1 x minus xn power nu n, where with a is some constant in a, constant in k, x1 to xn they are elements in L distinct, and this nu 1 to nu n they are the multiplicities of x1 to xn respectively, which are non-zero natural numbers. Check that the degree of L over K will not exceed degree factorial less equal to degree factorial. If f is of degree d, then degree factorial is d factorial. But before I prove that, let us recall little bit about the multiplicities. So also the notation which we keep using in this course later again and again, when I say v of a polynomial f in the field L, these are the zeros of f inside L. So those are x1 to xn. So this means there are different elements of L and all of them are zeros of f, and the degree of f is nu 1 plus nu n, which is obviously bigger equal to n because x1 is a 0 of multiplicity nu 1, xn is 0 of multiplicity nu n, and this nu i's can be computed easily without actually computing the factorization of f as follows, because this will mean that x minus xi, this factor, this is a factor of f, and to check that this is the highest factor of f, you just have to compute the derivatives of f. So f is here, f prime, f double prime, these are the formal derivatives of f, and f nu I and so on, and now you have to evaluate them at xi. So this should be 0, this should be 0, and this should be 0, and the first time you hit that is non-zero, that will be the multiplicity. So for example, if fi of xi is 0 but the derivative is non-zero, that means the multiplicity nu I is equal to 1. It is not more than 1, and so on. So that is a very effective way of computing the multiplicity of a 0 of a polynomial. Now let us prove Kronecker theorem. So, proof of Kronecker theorem. Proof of Kronecker theorem. So, first of all, we may assume f is monic. If necessary, you divide by the leading coefficient of f, and we are going to prove the assertion, proof by induction on the degree. Degree of f. Let us call this degree to be d. So, it is obvious that if d is 1, that means f is linear. That is, f is linear, and because we are assuming it is monic, then f must be of the form some x minus some x1 minus a, where a is actually coefficient of f, which is in k, because we are assuming f has coefficients in k, and therefore we are done, because in this case we can take L equal to k, and there is only one 0, x1 is a, and nu1 is also 1, and that's it. So in this case we know the assertion, we don't need to enlarge the field k at all. So now assume that degree d is bigger or equal to 2. Alright. So we have this polynomial f in kx, and we know that this is a PID, and therefore every element of this has a factorization into prime factors. So f has a prime factorization in kx, which is essentially unique up to permutation of the prime factors. So therefore definitely this f we have, because we are assuming it is monic, this will have at least one of the prime factor mu and maybe more. So this mu is a polynomial in kx, a prime polynomial. Prime means it's monic, and it is you cannot factorize anymore inside kx. So once you have this, then you look at form a residue class algebra. So k is here contained in the polynomial algebra. This is a ring homomorphism, and then you have gone modulo mu, ideal generated by mu, that is a residue class algebra, and this we know it is denoted by k small x, where the small x is the image of capital X modulo mu, and because mu is irreducible, mu is prime, it generates a prime ideal, and therefore it generates a non-zero prime ideal, and therefore, like earlier argument, this must be a field. So this kx is a field, since mu generates a non-zero prime ideal and hence maximal ideal in kx. Therefore modulo a maximal ideal, you always get a field. Therefore this is a field. And not also, where do capital X go here? Capital X go here to small x, but mu, where do mu go? Mu goes to 0, and this is a ring homomorphism. Therefore mu of x bar, this is 0, but bar is same thing as, it's because it's a ring homomorphism, it commutes with the polynomial, so this is mu of x. So actually x is a 0 of mu, that is x is a 0 of mu. And where do f go? F goes to f bar, but f bar is mu bar times some more factors, but already mu bar goes to 0 mod mu, so therefore f bar also goes to 0. So therefore definitely f of x, f is going to f bar, but f bar is nothing but f of x, which is also 0. Therefore this x is an element in Kx, this field, and it is a 0 of f. Therefore I can divide f by x minus x in this L prime, this is L prime. So this will be, f will be a multiple of this in L prime x. This x was a 0 of f in this field, therefore it looks like this, and monic, therefore G belongs to L prime x. This is also monic polynomial. Factor of a monic is always monic. So therefore now we are going to apply, and what is the degree? What is the degree of f in terms of degree of G? So we know degree of f, which was d, which will be equal to 1 plus degree of G, and therefore, and also we know dimension of L prime over K. L prime was Kx. This dimension equal to the degree of mu. Therefore I want to apply now. So therefore the degree of G has dropped. Degree G is 1 less than the degree f, equal to d minus 1. So by induction hypothesis, I can enlarge the field L prime to L such that so this L prime, L over L prime is finite field extension, and G will split into linear factors in Lx. So G will look like x minus x1 nu 1, x minus xn nu power n, where x1 to xn they are elements in L and distinct, and these nu 1 to nu n are their multiplicities of this one. But then f will also split into L in Lx, because f equal to x times x G, which is now you can, this x may be one of them or may be different. So therefore this also splits into linear factors in Lx. So that proves our assertion. Also the last assertion which says that the degree of L over K, this is the degree of L over L prime times degree of L prime over K, and this degree we know it is, so this is less equal to, this degree is altogether less equal to degree of f factorial. So this proves Kronecker theorem. So this completes This proves Kronecker theorem. All right. We will use this Kronecker theorem very often. So, as an example, let us discuss one example. For example, suppose we have this polynomial x square plus 1. This is a polynomial with real coefficients. Think of this as a polynomial with real coefficients. And what did we do to obtain the bigger field? So, what we did was we tried to find a factor of this, but this already is prime polynomial. Therefore, we go mod this Rx mod this ideal generated by x square plus 1, and one note that this is a field. This field is nothing but the field. So, in our notation it is R small x, where small x is the image of capital X inside this residue class R algebra, and but this field is isomorphic to C. There is an isomorphism from this to C. This is an R isomorphism, R algebra isomorphism. So, remember complex numbers that was defined by Hamilton around 1837, and Hamilton, because he was from physics, he thought complex numbers as a pairs of real numbers x comma y r square, and when they correspond to x plus iy. So, he thought as a pairs the complex numbers, but this description was due to Cauchy's, which was around 1847, 10 years later than that of a Hamilton, and it was based on the fact that if you take the real polynomial x square plus 1, this does not have real 0, this 0 set is empty. And also note that this description shows also that which was the order of the field of real numbers, it is lost when you go to complex numbers, because x square plus 1 is 0 in this field. That means x square is minus 1. But this is not possible, because on one side it is negative, on the other side positive squares have always positive order. So, therefore, one cannot extend the order of real numbers to the order on complex numbers. So, therefore, with this C is not an ordered field. So, this is a loss. We have extended the field R to the complex numbers by looking at the zeros of the single polynomial, and after that we will prove in this course of lectures that that's enough. Now, C is algebraically closed. That means every polynomial with coefficients in C has a complex zero. This we will prove in the due course of these lectures, but we will stop this lecture here now and try to see more examples in the coming lecture. Thank you.